Hi everyone, I'm Paolo Geremia and I work with ANGIS. Today I'm going to talk about a new free surface adaptive grid refinement method for marine applications. And this work was done in collaboration with my colleague Daniel Deising from ANGIS and Professor Kevin Mackey from the University of Michigan. So let's start off with a bit of background here. First of all, when it comes to run free surface flows for ship hydrodynamics, especially in case of large body motion with OpenFOAM, you need to rely on sometimes quite complex meshing strategies in order to fully capture all the different features that you want to have. This becomes sometimes difficult to automate in workflows when you have to run multiple cases or you have different attitudes of your body and so on. I'm not saying that it's not possible, it's certainly possible, but it requires some efforts from the user. And this is why we thought that probably a solution we could provide to this problem would be based on adaptive mesh refinement. And this is what the talk is all about today. And we will see also how this AMR, adaptive mesh refinement, will be implemented in Helix Marine using OpenFOAM libraries. And the main focus on this presentation is about validation cases. So here's the agenda for today's talk. Let me get rid of this. So I will start with a few words about the method itself, and then I will touch on a couple of the validation cases. And finally, I will draw some conclusion. So talking about the method, the AMR was developed for free surface flows in general. And we decided to extend it to add it to marine applications for ship hydrodynamics. In terms of the algorithm itself, the method is based on the XRF8 mesh cutter class. So it basically splits a parent cell into 8 children. It provides a first order field mapping. So this means that all the children receive the parent cell value, and it recomputes the, it prevents the refinement of non-hexahedra cells in terms of when it does the mesh mapping. So this means that AMR can be run on any kind of mesh. So it automatically excludes all the cells which cannot be refined, of course. It performs a recomputation of wall distance fields as required by the turbulence models, and it provides also an optimized algorithm for cell selections for the unrefinement in order to prevent successive refinement and unrefinement of the same cell. So it's optimized in this sense. This method was coupled to a 6DOF library that we being extensively employed in our Helix Marine software for several applications. For example, here we have seakeeping, so you can see here all the body travels with the mesh travel with the body, and this is how it works. So you can model the 6DOF, and it's based on a hard-fixed reference frame, rigid body formulations. It accounts also for added masses and inertias, and it couples to waves to foam for the wave libraries. We modified the relaxation zone, so we had an implicit formulation instead of default explicit one for more accurate results. Moving to the validation cases, let's start from this one. This is the KCS case 2.2a. It's an old validation case from the Gothenburg 2010 workshop. It's about calm water resistance. And here we have the ship in fixed position, even keel with a rudder, traveling at a constant speed, 0.26 Froude number. It's a model scale. and the length is about 7.2 meters, 7.3. The draft is about 0.3 meters. And here the objective was to run a mesh sensitivity study in order to see how the AMR behaves. So you can see here the coarse medium mesh after the AMR was applied. So you can see an extra refinement of it in the transom area and for the different grids here. As we keep the same setting, we just change the density, and we want to compare the results in terms of calm water resistance. So in terms of solver times, we ran from 10 hours to 15 hours to 42 hours for the 3 different grids running on 12 cores. And the mesh size after the AMR was applied was ranging from 0.7 million cells to 2.3 million cells for the fine one. You can see here from the graph, these on the x-axis, you have basically the refinement ratio between the different mesh sizes. So 1 means the fine mesh. This is 1.5 is about the coarser mesh, and this is the experimental results. You can see there is no monotonic convergence here, but the solver, the error reduces as the mesh gets finer and finer. So there is kind of a good sign here in terms of results and accuracy. Actually, we are within the 3% for the coarse mesh case. Looking at the wave elevation, you can see from the coarse to the fine mesh, the results are more or less similar. And moving to the 2 degrees of freedom, we have the same case. So the KCS with the rudder taken from the same workshop, Gothenburg 2010. The case is the well-known 2.2B, same scale, same dimension, and so on. The only difference with respect to the previous case is that here we're modeling 2 degrees of freedom, so the body is free to heave and pitch. And this is the resulting mesh you can see in the slide. So there is an overview. On the top, on the bottom, you can see the mesh after the AMR was applied. So you can see that there is an extra refinement in the fore and the aft section. So for a total of 1.3 million cells. So we are using a medium density grid size here. We ran the case with, okay, the background mesh was just 1.1 million. So there is only 200,000 cells of overhead using the AMR with 5 near wall extrusion layers for the boundary layer. We ran with a maximum CFL of 25 globally. And these are the Froude numbers we ran according to the test. The solver time was about 40 hours on 6 processors. And this is the conversion from one of the cases I picked up. So this is one of the 0.15 Froude number, lower speed. And in the dash curves represent the experiments. And here you can see, sorry, the dash black line represents the experiments, and the continuous line represents the CFT. And the 2 red and blue are the viscous and pressure components respectively. Whereas here on the right, we have a heave and the pitch. You can see here there is a good convergence and also a good matching of the results. In terms of hull motion, this is what you can see here. So resistance, resistance at the hull motion, you can see for the different speeds, there is a very good agreement. Same for the heave. For the trim angle, there is a small mismatch, the low and high speeds, and this is very small anyway, so a fraction of degrees. In terms of wave elevation, this is what you get. You can see that the wave characteristic increase as we might expect as you increase the velocity. And this is the wave pattern for the different speeds. So from the lowest to the highest speed, you can see here how the wave profile develops. Concluding, the method based on automatic adaptive mesh refinement, AMR, was coupled to a 6-DOF unsteady runs VF solver. which was applied to displacement hull for the water resistant prediction and motion of using a 16th library. The DUE technology is important because it removes the pain of defining a free surface refinement strategy, which is efficient for different operating conditions. So this makes the life of the engineer easier. It's easy to set up and to use because it can be automated in terms of scripting, and it provides a robust meshing and solution framework, which can be easily applied to different hull forms. In this particular case, the methodology was validated on a specific hull form, but we developed best practice for the background mesh to be creation. But in general, the method can be applied to any hull shape, including planing hulls, of course. So this concludes my presentation. Sorry. So if you have any questions, feel free to ask. Thank you very much for your attention. Okay, let me. Okay, I can see there are a few questions. Let's start from the, okay, it's the same. We can start from the bottom. What do you mean by first order mapping? I think this is the, okay, I will have to ask to my colleague Daniel Dicing, but I think it's related to the mapping of the interpolated mapped the velocity field when you basically apply the AMR. And then, so there is a mapping of the velocity, and then there is a pressure reconstruction to get a divergence-free flux. And so this is also available in standard OpenFOAM. Not sure if this answers your question. Is there any boundary layer? No. Okay, the boundary layer is applied to the hull. Yes, of course. The AMR is not touching the boundary layer. There is an offset around the hull. You can define some protected cells where not to apply the AMR. It's only applied to hexahedral cells. What kind of interpolation used for field mapping at refinement? This is a question I need to ask my colleague Daniel, so I'll leave it there. The CF number during the simulation can be increased to 25. Oh, okay. We do multiple outer correctors, and this coupled to some robust numerical schemes provides a robust solution. What about the polarization after refinement? Do you make decompose again? No, this is all done automatically. Again, this is a question for my colleague who implemented this. So usually we define a hierarchical in the composition, as far as I know, but again, I need to double check on this. So it's only important to define the number of processors here you need to define. Okay. Which criteria? We just define as a very simple criteria. So there is multiple criteria supported. In this particular case, we just use you just refine on the free surface. So we put a threshold for the alpha phase fraction, really. But you can define more fancy ones based on gradients and so on. Dynamic load balancing, no, Joel, not yet. This is something we need to work on. Okay. As I said, this one I will have to make a note and double check with my colleague, the kind of interpolation. Okay, I'm not sure if there is need to hand over.
Hi. So I think that now is my turn. Let me share. Apologies. Let me share my screen. So, good. Hi, everybody. Today I'm gonna describe some of the results that we got when we try to understand speed loss that was reported due to the installation of a sonar dome in an oceanographic research vessel. So we use OpenFOAM, we perform the simulations full scale, and right now we are collaborating with Professor Ino from Yokohama National University in order to include the performance of the propeller of this research vessel. This vessel was built in Japan back in 1981. It was, at the beginning, it had the capability to go to the Antarctica, but with time, with the years, it lost that capability. I think that it was related with the double hold structure. So now our research, Oceanographic Research Institute is using this vessel to do some bathymetry measurements in the Ecuadorian coast and Galapagos area. So the basic problem is that this vessel is around 70 meters, has a design speed of 12 knots with a draft of 3.6 meters. And back in 2008, it was added a sonar system in the lower part of the vessel. So in order to protect that sonar equipment, a dome was fitted on the hull, on the lower part of the hull. So as you can see, this structure, it has a triangular forward body shape, and on the back it has mostly a rectangular shape. And the dimensions is roughly 6 meters long and 3 meters wide. And it has a less than 0.6 meter protruding from the hull. And the basic problem that they had was that this vessel lost speed, the capability to achieve the 12 knots. And it was operating between 6 and 8 knots. So the main question was if the dome was the whole responsible of that speed loss. We interview the crew, we visit the vessel during a dry dock maintenance, we take measurements in order to prepare the CAD, the 3D CAD. And we found out that the propeller is a mouse series type. Because at that time, we didn't have more information regarding the open water characteristic curve. We used the Wageningen series B approximation. And the basic question was how we can make sure that our numerical simulations are reliable. So I contacted the propeller design back in 1981. It's a company that is still operating, that is Kamomi Propeller, and they kindly provide us the effective horsepower score that they use in order to design the propeller. So we use those data as a validation, as a reference data, especially the 12 knots data. After that, we had the opportunity to measure the torque acting on the shaft during sea trials back in 2018. So what we did, we performed numerical simulations using OpenFOAM, the version 7. We use the interphone solver, model the turbulence with the SST model with wall functions, And we generate the grid basically using the combination, the block mesh plus snappy X mesh. So this is the full model. The one that we include in our simulation doesn't include the appendages that are shown on the back portion of the hull. So we include the dome. We perform simulations without the dome and with the dome, including 4 grids. One, the coarser one had 0.7 million cells, and the finer one has around 12 million cells. We check that the Prism layer, our measure had some issues, especially close to the feature lines that we define. Regardless, we expect that this has a lower impact on the estimation of the shear stresses. We double check the grid convergence with the 4 grids that I mentioned before, and on the right, you can see how the force prediction evolving per iteration. So we believe like our numerical prediction converge to a value that is about 24.5 thousand newtons, and that if we compare that value with the data provided by the propeller designer, it's close to 2% of difference. We assess the grids, the fine to the coarse, and we estimate like the grid convergence index. So from the next results, we use the finer grid, considering that is within the expected error, and that we wanna capture this evolution of the flow around the dome. We compare the effective power prediction, the numerical one, with the one provided by the propeller designer, and we are within an error less than 5%. And so far, we have been able to confirm that the only presence of the dome is responsible of an increase of 38% on the effective power required to navigate 12 knots. Of course, that's going to reflect on the rotational speed that the propeller need to operate. And that 38%, it looks like the wave train has not a significant difference between the dome and the configuration without the dome as expected, because the structure is below the kill line. And we can assess that the pressure distribution, the front face of this dome, is acting as a stagnation area with high pressure, and that we were able to identify some vortex formation due to this dome structure that is propagated downstream, and maybe it could affect the propeller operation. That's something that we need to double check in the future. So about the conclusions, the dome is responsible for the 38% of increase in resistance force. We got some vortex structures that are shedding downwards, and that the propellers need to operate at a higher RPM. And what we plan to do in the future, we need to improve the Prism layer generation, complete the whole test matrix that we have designed, and after that, assess the wake field modification. At the beginning, we used the Wageningen type data, and now Professor Eno provides us with the data for the MAU propeller. The only thing is that if we want to improve the meshing, I think that I need to update the version of the OpenFOAM that I'm using on our HPC. And my only restriction is that I need to compile it with this version of OpenMPI using a singularity container. So if somebody has an advice on that, I will appreciate any suggestion. So thank you for your time. And that's where we are located in Ecuador. So any questions? Let me check. Okay, so regarding the questions, what kind of interpolation do you use? Okay, I think that that's not for me. Just to be sure, did you use two different mesh refinements for the simulations with and without the dome? If so, did you check for the effect deviation of the boundary layer? That's something that we need to look at. We try to generate the mesh only changing the cut geometry and keeping all the setup, the block mesh and the snappy settings the same. So I will double check that the effect of the presence of the dome on the deviation of the boundary layers. And regarding the vortex structure, we use the Q criterion. Yes, we use the Q criteria, and we just change the threshold from 20 to 40 in order to assess if there was any change of the value that we use. We are supposed to use a value, a positive value as threshold. Okay. So thank you for your time. And I think that is the turn of the next presenter.
Good afternoon, Mr. Wang. Mrs. Wang, sorry, are you ready to present?
Hello.
Yeah.
Professor? Yeah.
Yeah, you can come on stage, yeah. Thank you.
Oh, should I start now or at 10 o'clock?
No, you can start now, it's okay.
Okay. Let me share my screen. Okay, let's start it. Good afternoon, everyone. Thanks for attending my presentation. My name is Changchang Wang, a PhD candidate. Today, I will talk about a pressure-based compressible multi-phase cavitation solver in the OpenFOAM framework. Firstly, background and motivation. Bubbly flows are ubiquitous in many environmental, biomedical, and industrial processes. Yet a full understanding of the dynamics of these processes remains elusive. For example, in ship wakes, a large number of microbubbles from 10 to 100 micron are generated and persist for a long time. These microbubbles have a significant influence on oceanic environment, such as mass transport, absorption, and traceability of ship wakes. Another interesting example is the snapping shrimp. This kind of shrimp has two claws. One is small, used to grasp small prey animals, and the other is large. There is a rapid snapper claw closure. A high-velocity water jet is generated from the claw exceeding the cavitation conditions. With the ambient pressure recovering, these cavitation bubbles collapse, emitting shock wave and loud sound. They use these cavitation bubbles to stun or kill prey animals. Cavitation is such a kind of unique bubbly flows, which often occurs in hydraulic machineries. Also, computational modeling of cavitation has been pursued for years due to its complex flow physics involved, especially the multi-scale characteristics. The modeling of cavitating flow is still a challenging task. This chart shows the most popular method used in cavitation modeling, including their advantages and limitations. In particular, the transport equation model has been widely adopted and is mainly developed based on incompressible approach. However, to address the bubble collapse-induced shockwave and loud noise problems as seen from the stepping shape, it is necessary to develop compressible approach. Before I talk about the compressible approach, firstly, I'd like to present the results obtained from the incompressible approach. This is the experiment's data, and from the experiment, we can observe a phenomenon that when the large-scale cavity cloud shed downstream, the attached cavity begins to grow. However, after the large-scale cloud collapse, a sheet cavity shorten phenomena is observed, and this shorten is supposed to be caused by the cavity cloud collapse-induced shockwave. However, this incompressible result can predict the attached cavity growth, reinterjet development, the attached cavity breakup, and the large-scale cavity cloud shedding and collapse. However, there's no collapse-induced shockwave, and the sheet cavity shorten phenomena is predicted. And so, what's the compressibility effect in cavitating flows? In cavitating flows, local sonic speed is less than 5 meters per second, which is almost 2 orders of magnitude less than that of the pure phases. Furthermore, the abrupt phase change between the liquid and the vapor will significantly change the sonic speed curve, reducing the sonic speed. Consequently, in cavitating flows, although the incoming flow is always low speed and subsonic, when cavitation occurs, the incompressible incoming flows may result in supersonic conditions in local cavitation regime, and the associated strong shock wave could be generated. So what I do here is based on OpenFOAM framework, based on the original incompressible cavitation code and the compressible artifact code. I implemented the density and the temperature variation in the governing equations. What I do here, firstly, I derived the compressible phase transport equation with phase change, and then the pressure equation with the phase change. So I understand the mass transfer terms in the phase transport equations and the pressure equations, and then I implement the source term into the governing equations. To account for the temperature variation, I also solve the energy equation where the temperature in the flow field is also changeable. And to further consider the temperature effect, especially during the cavity cloud collapse, that would be high temperature, high pressure. So the temperature dependent vaporization pressure is also used in this computation method. And more detail about this solver can be found in the published journal paper. Here, I will not go more detailed about the implementation details. And then, firstly, this result is validated in terms of the, based on this hydrofoil, the NACA 66 mod hydrofoil. This is a popular hydrofoil section used for marine propellers. Furtherly, the cavity structures is validated. The periodic behaviors of cavity structures were predicted, especially in the process of the attached cavity growth. There is a re-entry jet development and the cavity breakup due to the complex cavity dynamics. There is a difference in the cavity size and the cavity shedding structures. However, after the large-scale cavity collapse, where agreement with experiments is observed, especially the shockwave generation and the sheet cavity shorten phenomenon. Then the pressure field and its spectral on foil surface are validated. Firstly, in terms of the pressure fluctuations, more detailed comparisons in one cavity cycle, like the cycle 2, is compared. During the attached cavity growth stage, attached cavity growth induces the pressure fluctuation at the cavity closure. Subdifference, and we can see subdifference at the cavity closure can be observed. This could be the cavity length fluctuations, and this fluctuation is also observed from cycle to cycle in the experiment observation. And then there is a large scale cavity cloud shading and collapse stage. A large cavity pressure peaks is predicted along with the rebound process. This is in agreement with the experiment measurements where lots of peaks and the pressure peaks are observed. Then about the spectral, we can see the delay rate between the numerical prediction and the experiment data with where a difference occurs at the cavity leading edge, and although there's a difference in the pressure magnitude, but the decay rate is still in agreement. This magnitude problem could be caused by the instabilities at the cavity leading edge. And the shockwave cavity interaction is studied. After the shockwave is generated, it will propagate in the flow field, both in upstream and downstream. The upstream propagation shockwave will interact with the cavity structures on void surface. For the cavity structure and pressure distribution along the void surface, we can see there is a shockwave cavity interaction. Shockwave collapse the local cavity as the cavity collapse enhance shockwave strength, coming with large transit load. Finally, to verify the properties of this shockwave structure, the shockwave jump condition is used to calculate the shockwave propagation speed. I calculate the shockwave speed using both the pressure field and the shock jump condition. And then these two shockwave speed is make comparison, and the difference between the two shockwave speed is within 5%. And then the compressible solver is validated against another experimental data, which has a typical rigid jet shading mechanism. It can be seen that this is a time average, the phase field and the velocity field. It can be seen that the time average, the cavity structures, and the velocity distribution are well predicted by both the incompressible and compressible method. This is not surprising because the incompressible method has been successfully used in cavitation simulation. However, when the comparison of the cavity evolution frequency in the unsteady process, we get the cavity frequency from both the pressure field and on the void surface and the cavity area. We can see, compared with the experimental data, the current compressible method can predict the unsteady behavior better. Firstly, we can see several peaks on the frequency spectral. However, for the incompressible method can only predict one peak, and there is still a difference between the experiment and the incompressible method, while the compressible method can predict 4 peaks agree with the experimental data. Now let's make a conclusion. So firstly, a pressure-based compressible multi-phase cavitation solver is developed. The current solver is validated using the experimental data for both the NICA 66 multi-hydrofoil and the Cat-Y hydrofoil. In terms of the cloud cavitation, in both the shockwave-induced mechanism and the re-entry jet-induced mechanism, and also the large-scale cavity cloud collapse induced shockwave dynamics is predicted, and its interactions with cavity is studied. For this cavitation solver, the further validation cases are being studied, and the improvement of the current modeling is also in process. Finally, I'd like to thank my supervisors in both Beijing Institute of Technology and the University of Minnesota. Thanks for the funding support from the China Scholarship Council. That's all. Thank you. I'm happy to answer any questions. Oh, I can see some question here. So I didn't go into more details about this. So there are maybe many physical models. Firstly, the cavitation model I use is the saddle cavitation model, which is adopted by many several groups, both in America and in German. This cavitation model is based on the heat transfer on a plate. So compared with other transport cavitation model, the saddle cavitation model takes into account the temperature difference. So I implement this cavitation model in my server. For the incompressible, I developed based on the compressible multi-phase change, compressible multi-phase change form in the OpenFOAM 4, because I developed this since 2016. So at that time, the 4 version is the latest version. So for this solver is based on that. And I also take a reference on the incompressible cavitation solver, the interface change form, and implement the details of the source term. I take reference to the incompressible phase change form. Yeah.
Hello, everyone. I guess I should take over the next speaker, or are there more questions? Okay, thank you. Thank you for your time. So my name is Ino Gatin. I come from the University of Zagreb in Croatia, and I'll tell you about a study that's ongoing here at the university about the comparison of VOF and level set, particularly specialized on the topic of self-propulsion in full scale. A little bit about the code. So the code that we're using and developing is called the Naval HydroPack, and it is based in foam extent. The main purpose of the study is to look into differences in terms of accuracy between VOF and level set. The reason why we want to do this is to make sure that we can use these methods interchangeably without loss of accuracy, in some cases when we need to do that. In this particular case, we are testing this on an example of self-propulsion in calm water. So our test case is a car carrier ship built here in Croatia in a former shipyard called Uljanik, for which we are lucky enough to have sea trial data. So we have actual measurements from the sea trial in full scale. It is a 200-meter vessel sailing at 21 knots. Before we move on to results, a little bit about interface capturing, which is the main topic here. So in the Naval HydroPack, we have 2 methods available. First one is level set, and the second one is volume of fluid. Here on the screen, you can see 3 methods. The first 2 are 2 flavors of the level set method, where in the first one you have the sine distance function, and in the middle one, we're using a tangent hyperbolic function for a level set. And on the last one is basically a step function which depicts the volume of fluid method. There are some advantages and disadvantages of both of these methods. We're going to go through them now. The level set method, the main advantages is that it gives you a sharp interface definition, so you don't need to worry about smearing of the interface, and especially the problems that this can lead to, namely the ventilation in some cases, especially for high-speed crafts, as you can see on the screen here on the top half of the image. Cons, well, the method is not conservative, so if you have violent resurface effects, you can lose or gain a considerable amount of volume, which is a problem. Volume of fluid, basically it's the opposite. So the advantage is that it is fully conservative. but with volume of fluid, we always need to battle the numerical diffusion that tends to make our interface physically thick. As you can see on the top half of this image, the green area is basically where you have a mixture of air and water, which is not realistic. So which method to choose? Well, that depends on the simulation that we are running. For example, level set is used in simulation where volume conservation is not critical, obviously. So as an example, you have calm water resistance or calm water self-propulsion. But on the other hand, where sharp interface is crucial, this is especially important for faster crafts where ventilation is a larger issue. Where free surface effects are non-violent, meaning that you don't have a lot of mixing and braking going on. So you wouldn't want to use level set for dam braking, for wave braking, wave impact simulations, because that's where you will have the largest conservation error. So as I said, examples, calm water resistance, self-propulsion, maneuvering, also simulations where you have non-braking wave simulations such as seakeeping in relatively mild wave fields. VOF, on the other hand, you will use VOF when volume conservation is very important, but where you can live with a little bit of smearing. Also, you will use it to simulate events where you have violent free surface effects like green water or dam breaks or wave break impacts. And for example, in green water applications, the conservation is quite important because you need to assess the mass of the water being shipped on the vessel accurately. So, but there are some cases in which we would like the best of the two worlds, or in another world, we need to run a combination of, say, self-propulsion and green water simulation, like the one you can see on the screen. So this is a free-running simulation of a naval vessel in stern quartering waves. We have the two actuator discs acting as propellers, but the vessel at one point ships a little bit of sea on the deck. And since this simulation is performed with level set, we cannot be sure that the mass is conserved and that the green water event is accurately captured. So in these cases, we would like to know that if we use VOF, we will still be able to evaluate the force acting on the hull accurately. In other words, we want to avoid having significant ventilation, which could ruin the accuracy of this method. So let's move on to results. These are a few images from the simulation. So we have conducted the simulation with VOF and level set with identical grids. These are pictures of dynamic pressure on the hull. You can see that the vessel is sailing in ballast condition. The bulb of the vessel is at the free surface level, which is not the design condition. So the vessel has a significant bow wave. And all of these need to be taken into account without having excessive ventilation at the bow. Of course, what's most important is to compare the numbers. So here we have a comparison between level set and VOF in terms of different items that we measure in the CFD simulation of self-propulsion. We have forces here, so FT is total force, which is the most important one, and you can see that the difference between VOF and level set is below 2%, which is good. Sinkage and trim have small absolute differences, but the values are really small, so the sinkage error is around 11%, still quite acceptable. What we need to know also is, since this is a self-propulsion simulation, the most important item is actually power being delivered to the propeller. And that's the last item here in the table. And you can see that the difference between level set and VOF is around 2.3%, which is acceptable. Of course, since we have sea trial data, we can compare these values against real-world measured values. And we can see that we have for a rotation rate of the propeller, we have around 7% error, and for power delivered to the propeller, 10 and 12%, which is on the high side. We have previously done this study with a different grid and have obtained better results. So at the moment, we are still in the middle of the study, and one of the things that we are doing right now is doing a grid convergence study. So these results that I'm showing you are done only on one grid, so this is an ongoing study. What we also done as an extension of the study is to check the same difference between VOF and level set, but using overset grid method. So we have a background grid and we have a forward grid that is body fitted to the hull of the vessel, and we want to know whether we can achieve a similar order of correspondence between the two methods, and also similar accuracy comparing to sea trials, which is very important. And this is related to another project where we will need to use overset extensively, probably with both methods. A little bit of comparison of the free surface elevation between level set and VOF, and also between front grid and background grid. So you can see on the top is the front grid, the one body fitted to the vessel, and on the bottom half of the image you can see the background grid level elevation, and you can see that they correspond quite well. Looking at it superficially like this, it's hard to see any differences, but although there are some. What's important for overset simulations is to have these two wave elevation fields to be as similar as possible on the forward and background grid, because this means that you are transferring the information back and forth in a correct way, which is very important to get the evaluation of the pressure forces on the hull accurately. In terms of numbers, total force difference between VOF and level set is around 3.2%, which is again acceptable, and similar differences for sinkage and trim in absolute terms. The propeller items, so the most important one is the power delivered to the propeller, so PQ here. You can see that it's around 3.4%, a little bit more than in the body fitted approach, but still acceptable. Comparing to sea trials, we have similar differences, around 7% for the rotation rate and between 10 and 13% for power. So to summarize, what we needed to do and make sure of is that we can use VOF and level set interchangeably in some cases without having to worry about accuracy of the forces being calculated acting on the hull. We have found that the differences are acceptable between the two approaches, and we have found that also with overset the differences do not change considerably. We have seen good agreement with sea trials, however we need to do some more work on that as well. For future work, as I said, the grid convergence study is underway, so we can have some uncertainty intervals for these values. And also, as I mentioned, this is a part of a bigger project where we will need to use overset more extensively, namely to resolve the propeller and the rotation of the propeller with the aim of measuring pressure pulses acting on the hull and causing vibrations on the ship. Thank you very much for your attention. I will be looking at the questions now. So I have a question from Fran Delic. Great presentation. Is there a significant difference in the computational time between level set and VOF method? That's an interesting question. Well, time step to time step, not really, but we have found that level set takes a bit more to converge the wave field. So the level set and VOF equations are coupled explicitly with the pressure equation and the momentum equation. And it seems that the level set equation needs a bit more to converge. The communication between level set and the pressure equation takes a bit more time, or more precisely, a larger amount of time steps to converge. which is a bit surprising. We're not sure exactly why, but again, these are two different methods that use different equations, and it's not entirely impossible that this is the case. So it's an interesting question, but VOF has turned out to be faster. That's the short answer. Let me try and see. Okay, Pauline Ferro. Thank you for a very interesting presentation. What is the inlet turbulence intensity? Do you maintain the sign distance function near the hull? Well, the sign distance function is maintained near the interface, so the hull is not the criteria, the interface is. We have a band around the interface where we make sure that the sign distance function is actually a distance function. Further from that, we don't care as much. The inlet turbulent intensity we typically use for these simulations is around 2%. I'll give it another half a minute for any remaining questions. I think that would be all of the questions. Thank you very much for listening. And if you have any other questions, please contact me via email. Thank you very much.